So we're still in section 2, but inside of section 2, we're just going to be talking about ranges today. So one of the easiest ways that we can evaluate a range is by using our graphing calculator. Look at the graph. So if you have your graphing calculator with you, I'd invite you to pull that out. So I can see these both at the same time. That looks good. Okay. So let's say we want to find the range for 2 times the square root of x minus 4. So one way that we can do this is use our calculator. So if I press the y equals button, I can type in this function into my calculator. So you'll notice that I already have something in the y equals. So I'm going to clear that out of there. If you have anything else in your y equals menu, I'd invite you to kind of clear out anything else you might have in there. Make sure you go down to check all the way at the bottom. Occasionally when you put your calculator in your backpack with the power still on, you'll end up with a bunch of gobbledygook in there that causes problems later when you go to graph that. So I'm going to type this in exactly as it looks. I'll do 2 times square root of x minus 4. And again, the square root button is on the left-hand side. You press second, and then it's the 4th number down from the second button. It's the second x squared command. Okay. So we've typed in our function now into our calculator. What we want to do now is to graph it. To do that, I'm going to pick the window, but to pick the window, I'm going to use the zoom command. So I'm going to press that zoom button there on the home row and pick just zoom standard. Everybody okay with that? So this is what my graph looks like. So if we're talking about range, which axis are we talking about, x or y? Y-axis. So if I look at this graph, I'm looking for the smallest y value or the lowest point on the graph, because the y's are the up and down part. So the lowest point on the graph appears to be right there, where my pointer's at. Do you guys agree with that? What is the y coordinate at that point? 0, right? Because that looks like the point 4, 0. Everybody agree with that? Okay. And because 0 is a y value that corresponds to an actual point here, should I put a bracket on the 0 or a parenthesis? A bracket. Everybody agree with that? Because there's actually a point that has 0 as its y coordinate. It's that point where my cursor was at. Everybody okay with this half? All right. Now, what is going to be the highest point? There isn't one, because the graph continues to increase as we go to the right. Everybody agree with that? So the upper bound we'll write is positive infinity, or you can just write infinity. Either is fine. I put positives in front of it because it helps me make sure I'm putting my infinity in the right spot. And then that obviously always gets parentheses. Everybody okay with that idea? So the calculator can really kind of help inform us on the ranges, because sometimes these are difficult to determine by hand. Let's just, for the sake of showing that, let's show how we can determine this by hand also. Everybody ready for this? We're going to be doing the same thing. We're just going to be doing it by hand. So what I'm going to do is I'm going to start with my original problem, and I've just replaced the f of x with the y. And the process I'm going to use is very similar to the finding the inverse process that we learned about in our Algebra 3-4 class. So if you remember, if we want to find the equation for the inverse, what we do is we first solve for x, or get the x by itself, and then we swap the x and y variables here. What I'm going to do instead is I'm going to start by getting the x by itself, and then I'm going to analyze what I have after that. So there is no swapping the x and y variable when we're looking for a range, but I am going to just get the x by itself, like we would have done when we found inverses last year. So what's the first thing I would need to do to get the x by itself in this function? Eventually I'm going to square both sides, but I'm going to want to get rid of this part first. And because this 2 is being multiplied to the square root, to move it to the other side, I would divide both sides by 2. Everybody good here? Now let's look at what we have. Bless you. We have y over 2 is equal to the square root of x, right? Or the square root of x minus 4. What is the smallest, or what can we say about the square root of x minus 4? What kind of number is that going to be? If I take the square root of something, what kind of number do I have to get back? Brian? Yeah, really a little bit more specific than that would be non-negative. You can get 0 also, but that's right. So that part is always positive, or non-negative is really what we should say, because we want to include 0 there. Everybody okay with that idea? So what can I say about y over 2 then? Well, it's got to be non-negative also, right? Because if y over 2 is equal to the square root of x minus 4, which is always going to be a non-negative value, because if I square root a number, in the domain anyways, I have to be getting 0 or something bigger. Everybody okay with that idea? And if I multiplied both sides by 2, I would just have that y has to be greater than 0. Which is exactly the range that we had determined by looking at the graph. Kendall? So if I look at the square root of x minus 4, if I take the square root of any number, the result I'm going to get is something non-negative, right? I can't get a negative number to come out of a square root. So the way I write that with an inequality is that that square root has to be greater than or equal to 0, right? Because that's where all the non-negative numbers live, is on the right side of 0 on the number line. Does that feel okay? Matt? Yes, I think that's probably safe to say. Yeah, yeah. So the number here and what's happening there doesn't matter in regard to the inequality. Now, if you're doing something weird like multiplying by a negative, that would be a different story, but that's beyond the scope of this class. If something's being added or subtracting, that doesn't really change what's going on because the dominating part of this is the square root part, right? Doesn't matter what you did to the number before that. When you take the square root of it, the only kind of number you're going to get back is a non-negative, provided that you're picking an x that's inside the domain, which is an assumption we're making here. Everybody okay with that idea? Let's do another. Sound good to you guys? And again, we'll do that other one both ways. So this time we're going to do 3x over x plus 2. So I'm going to do it first on the calculator. So again, I'll start by pressing the y equals button. And then I'm going to clear out what we just did. And now there's two ways that I could type this into my calculator. I think the easiest way is to use the fraction command. So if I press alpha and the y equals button, that opens up the fraction options. The one that I'm probably going to want to use is the numerator over denominator form. So I can type this in exactly as it looks on my sheet of paper, so I know that I've typed it into my calculator correctly. Alternatively, you could do the same thing with division, but you have to be a little bit careful with your parentheses. To type this in with just using division, I'm going to need to make sure I have a parenthesis around the entire numerator, and then a parenthesis around the entire denominator. Either of these is going to give us the exact same graph. But in my experience, it's very easy for students to forget the parenthesis doing it the second way. Whereas if you use that fraction command, it's really hard to type it into your or it's a lot harder to type it into your calculator incorrectly from forgetting a parenthesis. So again, to access that fraction command, you do alpha and then the y equals button. Okay, Vinny? Okay, and depending on the age of your graphing calculator, that shortcut may or may not be built in, but given your guys' age, that's been a shortcut for a while, so I'm guessing that most of your calculators is going to have that shortcut built in, and it wouldn't be an issue. If you have the rechargeable kind, certainly it would be. So if your calculator is is a charging one where you don't have to buy physical batteries for it, I'm pretty positive that's a shortcut built in. If you have an older calculator that still requires batteries, that might not be an option there. Okay, so again, I'm going to graph this. Typically to graph these things, you just want a standard window. So if you do zoom and then standard, it'll make sure your window is set. So this is my graph. Everybody okay here? Okay. So, first things first, we're looking for ranges. Do you see a lowest point on this graph? Yeah, not really. It seems like it's going down forever, so the lower bound would certainly be negative infinity. Do we see an upper bound on this graph? highest point on this graph. Positive infinity. Is this what I've written correct? It's not in this case. What is the issue, though? Are all the y values used in between negative infinity and positive infinity? No, right? It looks like there's maybe something missing here in the middle. Everybody kind of see that? So instead, what we're going to end up having is something like this, where our range is going to be built into two pieces. Everybody okay with that idea? So we have a range for this part of our graph, and then we'll have another range for this part of our graph. Everybody okay with that idea? So let's look at this piece first. Okay? So if I look at the highest point on this piece, it looks like it's about what value? 3. I agree. And if I look at this part of our graph, what looks like it's the lowest value? 1, 2, 3. I don't know. Looks like 3 to me. I know it's hard to see from back there. It's a lot going on. But this is pretty typical. Does anybody remember what this kind of function was was called from Algebra 3-4? This had a name. Started with an R. Matt? Okay. Yeah, let's hold on 1 second on that. Does anyone remember the name for this kind of function, though? We saw this in Algebra 3-4 last year. We definitely did these on test. Start with an R. A. This is a rational function. Remember that rational functions often have vertical and horizontal asymptotes. That's what's going on here. So this has a horizontal asymptote at y equals 3 and a vertical asymptote at x equals -2. Now this one was a little bit trickier to kind of determine the range by looking at the graph because of the presence of the asymptote. As Matt pointed out, if you look at the actual xy table on the graph, it looks like the minimum y value over here is like closer to 4 than it is to 3. That's a little bit tricky. If we do this by hand, we kind of remove that possibility. So let's take a look at doing this one by hand. So if I'm doing this by hand, again, basically what I want to do is start getting the x by itself. So what would I want to do as my first step to kind of get the x by itself? Anybody have a good suggestion here? So think back to 2 years ago in geometry. This kind of problem had a special name. This problem type started with a P, PR, PRO, PROP. You're in the wrong class. This is a proportion. Does anybody remember the first step to solve a proportion?
Yeah, the order.
Starts with a C.
Oh, I thought we
Cross multiply. So that's what I would do first here is I'm going to imagine y as y over 1, and then I will cross multiply. Everybody okay with what we've done there as our first step? Then I'll distribute the y through. Everybody happy to hear? Again, we're trying to get the x by itself. So what would I want to do next? I would want the x's together on the same side. I wouldn't want to divide to get them together. Subtract xy from both sides. That'll get the x's on the same side. Can I subtract xy from 3x? No. Right? Because they are not like terms. Hannah and Janice, can you guys stop talking, please? Okay. Everybody's happy so far to hear. Now, I have x's in two different spots now. I have 3x and I have xy. I can't combine them because they're not like terms. What should I do here? Matt? Well, the problem is that I don't have a y here. So if I try to divide the y, I'm going to have 3x over y, which is going to be a little bit of a problem. Lexi, you had a suggestion? That's what I would want to do here. Notice on the left-hand side, I have a 3x and an xy, both of which contain a factor of x. So if we factor that out, we now have an x in one spot, right? So I took a greatest common factor of x out of the left-hand side. Kendall? Well, so here I had y times x plus 2. So I used the distributive property. I multiplied x and y together to get xy, and I multiplied 2 and y together to get 2y. So they are together, yes. All right? And then again, we're trying to get that x by itself. We've gotten the x now into one place, right? What do we need to do to continue? Kendall? Divide by what? Excellent, by 3 minus y. So if I look at this now, are there any values of y that I can't have? Notice that I have y in the denominator of a fraction, right? So I know that 3 minus y cannot equal 0. Stretch? Okay. If I solve this for y, I would subtract both sides by 3 and then divide both sides by -1. And I find that y cannot equal 3. If I rewrite this then as an inequality, I know that's the same thing as y is less than 3, or y is greater than 3. And then writing this as an interval, I know I have -infinity to 3 union 3 to positive infinity, which is what we observe by looking at our graph. Questions on what I did here? So again, when it comes to finding one of these ranges, either of these two methods I think are appropriate for you guys, whichever you feel better about, whether it's using your calculator or you doing it by hand or doing one in support of the other. Like oftentimes it's helpful to look at the graph first, and if you're not sure what's going on, as in this previous example where it was a little bit ambiguous in terms of the y value that was missing, doing the by hand method is often informative as to whether that's one value that's missing or multiple y values that are missing, right? Is everybody okay with that idea? Good. The next topic that I want to talk about then is about something called continuity. And we're, in this class, going to give a pretty informal definition of continuity, mostly because the precise definition of continuity requires calculus, which obviously this class precedes. But the definition we're going to give instead is going to be informative and really practically useful, but really you couldn't do any proof with it, but that's beyond the scope of this class anyways. But if you take a calculus course, this will certainly be a major topic in the early parts of your first year calculus course. And maybe I shouldn't say if, I should say when, right? Yeah. So we'll say a function, and the function I'm going to refer to is going to be called f of x, is continuous on a given interval if the function does not appear to break, and I'll put quotes around the word break because that's not a technical term, at any point on that interval. So basically we're saying if you can draw that part of the graph without picking up your pencil, then the graph was continuous over that part. Everybody okay with that? If you can draw the entire function without having to pick up your pencil, we'd say the graph is continuous, or we'd say that function is continuous. Okay with that idea? And in your Algebra 3-4 class, we graphed some things that were continuous functions. A linear function is a continuous function. You can draw a diagonal line without having to pick up your pencil. A quadratic function is continuous. You can draw a parabola without having to pick up your pencil. Polynomial functions are continuous. You can draw a polynomial without having to pick up your pencil. Radical functions were continuous. You can draw a square root or cube root function without having to pick up your pencil. Exponential functions were continuous. You can draw the entire exponential curve without having to pick up your pencil. Logarithmic functions were continuous. You can draw your whole logarithmic curve without having to pick up your pencil. Rational functions were not always continuous. Many times in a rational function you had to draw it with 2 pencil strokes because you had a vertical asymptote that wouldn't allow us to connect our graph all the way through. That was the first and only function we saw in Algebra 3-4 that was not continuous over the entire, or over the function's entire domain. Does that help a little bit in terms of like what we're looking at when we talk about continuous or not? So these breaks in our function we call discontinuities. And there's 3 types. The first type that you might remember from your Algebra 3-4 class was something called a removable discontinuity. So if you remember, this could happen occasionally when we're dealing with rational functions. What a removable discontinuity looks like is a graph where there's some point missing on the curve. The way we represented that missing point on the curve was with like an open circle. So for example, this could be the graph y equals squared minus 4 over x minus 2. I think would give us basically that graph. Yeah, I mean, pretty close. Maybe more like this. That's probably a little bit closer. Would be something like that. Now, just for clarity's sake, notice that this point here is not a point in the domain, right? Because there's no x value there. We still would call this a removable discontinuity if, say, we did put an extra point on there at that missing x value, but that point wasn't on the curve. Again, because you'd still have to pick up your pencil to draw this. So I can draw it to here, then I have my gap, I can put my point in, and I can go back and finish the curve. Have to pick up your pencil to do that. Or if there was no point elsewhere, I can draw the first part of the curve, have to pick up my pencil, and then I can draw the second part of the curve. Everybody feel okay about visually recognizing or a removal of discontinuity. There was a second kind that we saw last year. It was called an infinite discontinuity, but we didn't call it that last year. Last year we called it a vertical asymptote. You can use those two terms interchangeably in this class. I wouldn't fault you for that. But those are basically referring to the same thing. And again, something that might look like this would be y equals 1 over x minus 4 plus 2. Would probably look something similar to this. Hopefully we remember vertical asymptotes for sure from last year. We spent a lot of time when we dealt with rational functions talking about those vertical asymptotes. And there's one more kind of discontinuity that we have not seen so far, or you've probably not seen so far, I should say. It's called a jump discontinuity. So what a jump discontinuity looks like is maybe something like this. Where the graph like jumps up in value, like all of a sudden the point that you'd be expecting to see next is, been vertically translated either up or down. That there's a jump in the graph. Everybody okay with that idea? So notice here that at one location I have an open circle, and the other location I have a closed circle. Everybody can see that? Does it matter in calling it a jump discontinuity which one of them is open and closed? No. Everybody okay with that idea? Does it matter if they're both open? No, not really. Does it matter if they're both closed? That does matter. Why would both of them being closed be a big deal? Would this graph still represent a function if both of those points were closed? Why not, Sophia? How would you check to see if a function or if a graph represents a function? What did we do to check that? We did that earlier, like last week. Does anyone else remember what we used to check to see if the graph of something is a function? 3 letters. VLT, good, Hallie, a vertical line test, right? If both of those points were closed, we would fail a vertical line test and this would no longer be a function, right? So just if you're drawing an example of a function with a jump discontinuity, you have to make sure that what you're drawing is a function, in which case you can't have two closed circles at those ends. Is everybody okay with that idea? Okay. So I'm going to just graph a few things on the calculator. And then we'll look at to see whether they are, or what kind of discontinuity they are. Okay? So let's start by doing y equals 2 over x squared minus 4. So to type this into my calculator, the easiest way to do that is to press alpha, y equals, pick that first fraction option, and I'll have 2 over x squared minus 4. And then to graph this, I'm going to do zoom standard. So, when we look at this, do we see any discontinuity? Brian, you're shaking your head, yes. What kind of discontinuity do you see? Sections of the graph. Good. So, that's correct. 100% agree with that statement. Which of the three kinds of discontinuity do you see happening here? Was it a removable? Good. And how many infinite discontinuities do you see? 2. So there's one that happens right here, and then a second one that happens right here. Everybody agree with that? And if we were to estimate where those happen at, it looks like -2 and +2. Everybody okay with that statement? So one way we can do is we can describe the discontinuities happening, right? We said what kind the discontinuities were, and we said where they're happening at, which x values those discontinuity occur at. Everybody agree? Alternatively, we could describe the continuity of the graph. So initially what Brian says is he sees 3 continuous sections of the graph. You could also say, you could also talk about the continuity. So we could say the graph is continuous at those 3 sections. And if the discontinuities are happening at -2 and +2, the graph then is continuous at all the sections in between those. So on the left end, we have -∞ to 2. In the middle, we have -2 to +2. And then on the right, we have +2 to +∞. So either of these two descriptions are describing the same graph. Everybody agree with that? Okay. Let's look at this graph. So I'll go back in. I'm just going to edit what I had before. So if I put my cursor in the numerator denominator and press clear, it'll just clear the numerator denominator. That saves me from having to go back in and recall that fraction command. But if you cleared the whole thing, that's fine too. If you press clear twice, I think it'll clear the whole thing. And you could start over from ground zero if you like. whatever NBD. That's short for no big deal. Just helping you with your lingo. So let's look at the graph of this. So we'll do zoom standard. Do you see any discontinuity? No. If we look at the function, should there be a discontinuity? Well, is there any values of x that you shouldn't be able to have? Yeah, there should be a problem, right? The domain of this function shouldn't include the value -3. Everybody agree with that? So let's see what's happening. I'm gonna zoom in really tight here to around the point where -3 is. So I'm just gonna do this with my window. Well, -3 plus 3 is 0. And we know that we can't have a 0 denominator. And let's do that. Now if we look very carefully, do you guys see this? There's a little tiny gap in our graph. Notice there's a little spot missing. Hard to see it if you didn't know to look for it. How did I know to look for it? Because I had an x in the denominator, and I didn't see any discontinuity, but I knew there should be one there somewhere, because there are values of x that I know aren't in the domain, because I had x's in my denominator. So I went and started looking for it. In general, though, in that situation, if you can't see the discontinuity, what kind is it probably going to be? Removable. Okay. So I can say that I had one removable discontinuity at x equals -3. Or I could say the graph was continuous on the interval -infinity to -3, and then -3 to positive infinity. Again, it's conveying the same information. It would depend on what kind of question you were asked on how you'd want to answer something like that. And then we'll do one more. So I did x cubed minus 2x squared plus 3x. Notice there's no denominator here. I'm going to do zoom standard. It's a graph. And I have this. Do we see any discontinuity here? No. If I look at the function, there be any discontinuity? No, because I don't see any square roots. I don't see any denominators. There's nothing to really restrict my domain here. So I am pretty positive we have no discontinuity. Or I could say it's continuous from -infinity to positive infinity. What kind of function is x cubed minus 2x squared plus 3. That has a name, right, for that kind of function. We talked about them a lot in Algebra 3-4 last year. Starts with a P. P-O. P-O-L. Polynomial. And all polynomials are continuous functions. So,
Excuse this interruption.